Good morning, everybody. This is going to be the class of the Friday, the 13th of October, because most of you voted that this day is going to be learned in this way. So this is the video of the class. It's supposed to last more or less the same as a normal class. In this case, you don't have me in front of you, so we don't have interactions. So I expect you to write down your notes, to write your questions and doubts that you can ask me either in class or in the forum of the subject, or maybe in an email, a private message through the virtual campus. But please ask me the doubt you have, because I cannot answer the doubt right now. So if you remember, we were seeing topic 3, and we started seeing the logic families. We saw some other parameters that you already know, such as the times, the switching speed, the rising and fall time, and also the propagation times, the high to low propagation times and the low to high propagation times, always measured comparing the input with respect to the output. We also saw the integration capacity, that it has to do with the area and the power consumption of the transistors that are behind the logic gates. According to the quantity of gates we have in a chip, in an integrated circuit, we have these 4 scales of integration: the small scale, the medium scale, the large scale, and the very large scale integration, that is more than 10,000 gates in a chip, and it is the most widely used nowadays. We saw the ideal logic family, the ideal inverter, and I told you that these graphs, this characteristic transfer, can be used to be compared with commercial gates. When we want to buy a gate, we can compare its transfer characteristic with the ideal transfer characteristic. The more similar they are, the better the gate we want to buy is going to be. And we finished the class seeing the logic families. We saw in a rough way the logic families based on bipolar transistor. We have the most ancient, that is quite obsolete right now, that is the RTL family, that is based on resistors and bipolar transistor. And we saw that here, if we look at here, we have the inverter we made with the bipolar transistor, and this is the inverter that we are going to do in practice 3, in the simulation part and in the laboratory part. We also see an evolution of the previous family, that is the DTL family. The D comes from diodes, because this family incorporates diodes to the circuit. In this case we have an AND gate, and in this case we have a NOR gate. You can see that we have 2 inputs in the logic gate in both cases. The last family based on bipolar transistor is the TTL family. This is the most used family nowadays, based on transistors, in bipolar transistors, sorry. It's an evolution of the DTL family. It incorporates diodes, but besides a lot of resistors, a lot of bipolar transistors connected in this way, and a special case of a bipolar transistor with 2 emitters. We are not going to see this family deeply, because we are more interested in families based on MOSFET transistor. I told you that the MOSFET transistor are the ones that are used in logic gates and in chips, processors, memories, GPUs, etc. nowadays, because as we saw in the last session, in order to design a logic gate with MOS transistors, in the case of the NMOS family and in the case of the CMOS family, we only need transistor. we only need NMOS transistor and we don't need resistors, diode, etc. as in the previous case of the bipolar transistor families. We saw in the class the examples of two inverters. The first inverter belonged to the family of NMOS. In the NMOS family, we have enhancements NMOS transistor in the base part and a depletion NMOS transistor in the load part. We saw that the load part is the upper part of the circuit and the base part is the lower part of the circuit, and just in the middle point between the base and the load we have the output of the circuit. This is the output. This is not a branch, it's just a point in which we measure, but it's not a branch. Okay, so well, we know that they are NMOS because we have the arrow leaving the transistor, not entering but leaving the transistor. We saw how this NMOS inverter worked with when the input was a logic 0. We have here the reasoning, the development of the equations, and we saw as well what happens when the input was a logic 1. A logic 1 was the supply voltage. In the example we saw, supply voltage was 5 volts, but it may be another number of another number of volts. Sorry. Here we have the conditions to determine if the transistors are either in cutoff, in ohmic region, or in saturation region. You can see that the equation may seem complex, but you have this equation in topic 2 in the end. So if you go to this topic, you can check the conditions. We need to be in either region and the value of the currents for those regions, for the depletion MOSFET and for the enhancements MOSFET. So if you see the conditions in the circuit here, you can compare with the condition in the tables and you can understand if the transitions are in ohmic or in saturation. And once they are in ohmic or in saturation, you select one or another equation for the currents. Finally, you are going to see if they are in ohmic saturation, the value of the output, and if they are consuming or not power. Here we saw a summary of both inverters, the NMOS inverter and the CMOS inverters. Okay, and we can see what happens when the input is 0 or 1 for both cases. We have the inversion in the output, and we have here the regions of working of every situation. So we can extend this to the case of more complex logic gates, as we saw in the end of the class. We are going to continue with that. We are going to remember how to design this logic gate using the NMOS technology and the CMOS technology. We can use the summary just to know in which region are going to be the transistors of the base and the transistor of the load part. Okay, it doesn't matter if we have several transistors instead of one. We can use the same condition of the table. So firstly, we are going to remain this logic binary operation that we show. They were the basic logic operations, and the first one was the OR gate. This is called the logic sum, and the symbol was the plus of the sum. It's not a normal sum. You have to take into account that it is the logic sum. So according to the combination of the inputs, the output is going to be the following. So we have two inputs, so we are going to have 4 combinations. You are going to learn to do this because we are going to use this a lot in the subject. So how this logic gate works? We have a 1 in the output if A or B is 1. So we only need one of the input to be 1 in order to have a 1 in the output. So here in the first combination both inputs are 0, so the output is 0. But in the 3 remaining combinations, B is 1 here, A is 1 here, and both are 1 here. So we accomplish this condition, one or the other are 1, so the output is 1. Sorry, I didn't draw this well. This way. So we also show the AND operation that is called the logic product. And the symbol is this one. And again, don't confuse this with the product. It's the logic product, and this is a logic operation. Here, the output is going to be the following. These are the combinations for the inputs. The inputs are binary, of course. So the output is going to be 1 only if A and B are 1. Sorry, I have to. This is not like this, it's like this. So the only case in which both inputs are 1, A and B, is the last case. So here we have a 1, and in the other combination we have a 0. If you don't understand this, just ask me, okay, in class, because it's very important. And the last logic operation is the NOT. It's the most basic. It's the logic negation. Logic negation, and we are going to negate a variable, just putting this line over the letter. Another names for this operation is the complement, the logic complement, and the logic inversion. They are all synonyms. And here is really easy. We are going to have the opposite. If A is 0, the output is going to be 1. If A is 1, the output is going to be 0. So the output is the inversion or the negation of the input. Note that we can negate twice. If we negate twice, we have again the input. I mean, if you have 0 here and you put an inverter, you are going to have 1 here, but if you put another inverter, you are going to have again 0. So if we negate twice, we are going to have the original value. This is important. And the double negation is expressed with 2 lines over the variable. So we saw the using the NMOS families, we saw this circuit. I'm drawing the base of the NMOS family. The input is connected here, and we are going to have 2 inputs, one here and the other one here. Note that these 2 transistors are connected in parallel, okay, because they share the same terminals, the same nodes. In fact, this is ground, so we can draw it this way. So this is the base, and in the load, in the NMOS family, the load is going to be always an NMOS depletion MOSFET, in which we have always a channel. The channel is created in the manufacturing process, remember. The gate and the drain, the gate and the source are short circuit. So the value here is the same as the value here. It doesn't mean. Here we have the gate, here we have the drain, the source, gate, drain, and source. And we are going to call the transistor like A, M, B, and M, C. So we are going to analyze what happens with this circuit according to the value of the input. So we are going to use this table. Transistor A, transistor B, transistor C, and the output. The combinations of the input are going to be these ones. And we are going to analyze the circuit. In the transistor NC, the low transistor, we have that the voltage between the gate and the source is 0, because they are the same points. Remember this. So we can conclude that they are the same. I'm going to delete this. So this means that this voltage is going to be higher than the pinch of voltage, and we are going to have always a channel created here. So what happens? In the first case, both transistor A, I forgot to draw here the output. In the first case, both transistors are in cutoff, because voltage A is equal to voltage between the gate and source of transistor A, and input B, the input V is the voltage between gate and source of transistor B. So if both are 0, they are smaller than the threshold voltage, so we don't have channel. If we don't have channel, they are in cutoff. So here in this combination, they are in cutoff. What happens when the base is in cutoff? We can look at the summary we have here. When the base is in cutoff, the low transistor is in ohmic. So this transistor is in ohmic. We have these both ways cut. So with this graphical method, the supply voltage can reach the output. So we are going to have a 1 for this combination. What happens with this combination? Input A is 0, so the transistor is going to be cut off, but input B is 1. So if it's 1, we are going to have a channel in the transistor B. What happens when we have channel here in the transistor B? We can ignore now transistor A because it's in cutoff. So if we remember, if this transistor is in ohmic, the load is going to be in saturation. So this is in ohmic, and this one is in saturation. In this case, both transistors are conducting. So we cannot use the graphical method of the ways, but we have to know the following. In this case, voltage between drain and source of transistor V is 0. Okay? This is 0. This is 0, the point between this and this. And so this is 0. So the subtraction is going to be 0. In the drain we have the output because they are the same connection. Okay, this is a cable. And in the source we have ground, that is 0 volts. So the output is 0. Okay, 0. We are going to see the other case. In this case, in the third combination, B is in cutoff. We know that A is in ohmic because we can follow the reasoning we have just seen for the previous combination. And if this is in ohmic, the load is going to be in saturation, and we are going to have a zero because right now the voltage between drain and source of transistor A is zero, and we can follow the same reasoning. The output is going to be zero. And for the last case, transistor A and transistor B are conducting and they are in ohmic. So if the base is in ohmic, the load part is going to be in saturation. Okay? You can check always this table, okay, to reach this conclusion. So in this case, both the voltage DSA and the voltage DSB are zero, so the output is going to be zero, following this reasoning here. So this output is just the opposite of the OR gate, okay? So it is called a NOR gate. NOR gate. So if the OR gate is A or B, the NOR gate, that is just the opposite, is going to be the OR gate negated. It's just like using an inverter after the OR gate. So we are going to see what happens with the equivalent circuit, but for the MOS example, for the CMOS example. We are going to delete all of this. Sorry. Okay. And now we are going to design the same circuit, but using the CMOS technology. So the inputs that are in the base part of the circuit, the base transistor, are exactly the same that in the MMOS example. We have here the input A, and we have here the input B. So note that it's exactly the same base part of the previous case, of the MMOS family. Now we have to build the load part. This is the base, and this is the load part. Note the following. CMOS, the word CMOS, the letter C, comes for complementary. So we have to do in the load part the complementary of this base part. The complementary of an MMOS transistor is going to be a PMOS transistor, and they have to be connected in the complement way of this connection. This connection, I told you that is called parallel, because both transistors share the same nodes, so they are in parallel. So the complementary parts have to be in series, one transistor after the other. I'm going to show you. So here we're going to have a PMOS transistor for this input, and a PMOS transistor for this input. And sorry, because I draw this not in the right way. The arrow is entering here. The arrow is entering here. Okay. Sorry, it's the first time I'm using the table for doing this. I'm not very fast. So here we have the complementary of the other transistor, and here we have the output just in the middle between the load part and the base part. This is going to be the AMOS, the BMOS, the APMOS, and the ABPMOS. This is the source, the gate, the drain, the source, the gate, the drain, and here we have the drain, the gate, the source, the drain, the gate, the source, and they are in the opposite sides when comparing the PMOS with the NMOS, because we saw that we have to invert the voltages in one case with respect to the other. So now we can build the same table as before, but now we have 4 transistors. And the output. So we are going to analyze all the combinations we have. Sorry. So in the first case, both transistors in the base have a 0. If both of them has a 0, they are going to be cut, because the voltage GS of both transistors are not going to reach the threshold voltage, so they are going to be cut. What happens with their complementary transistor? So we can check the table. In the CMOS technology, it's really easy, because if the base is cut off, the load is going to be ohmic, and if the base is ohmic, the load is going to be cut off. It's really easy to calculate without looking at the table. So we are sorry, this is the here. So in the first case, I told you that I'm going to close this one. Sorry. In the first case, both are in cutoff, so their complementaries are going to be in ohmic. And what this means? It means that the output is going to be 1. Why? Because we can use the graphical method of the waves. I'm going to use a smaller. Here, this transistor is in cutoff, so we don't have channel. B is in cutoff, so we don't have channel. The transistor in the load are in ohmic, so they have channels. So the voltage, supply voltage, can reach the output. So the output is going to be 1, because a logic 1 is near the supply voltage, or even the supply voltage. Remember what a logic 1 is. So we are going to analyze the other combinations. In the second combination, we have that the A input is in cutoff and the B input is in ohmic, because it's a 1. So their complementaries is if A transistor is in cutoff, its complementary transistor is going to be in ohmic, and if B transistor in the base is in ohmic, its complementary transistor in the load part is going to be cut. So we are going to see again the ways that are open and the ways that are closed. In this case, we have a 0, and we can see why. We have this way cut, but this is open, okay? And we have this transistor, the PMOS B, closed. So supply voltage cannot reach the output, but the ground can use this way to reach the output, so it's going to be 0. We just have to check if it's the supply voltage or is the ground voltage the one that reaches the output to know if we have a 0 or we have a 1. So the next case. In this case, transistor A is in ohmic because it's a 1, and transistor B is in cutoff because it's a 0. So the complementary transistor of A, the PMOS, has to be in cut, as the complementary transistor of the NMOS, the PMOS, is going to be in ohmic. Always the ohmic or cut. Always the opposite when comparing both transistors. So in this case, we are going to have a 0. Why? Because of this, we have the B transistor cut, but the A transistor open. And here in the load part, we have the A PMOS cut. So the supply voltage cannot reach the output, but the ground voltage can use this way to reach the output. So we have a 0. I think that this is quite easy once you know how to interpret ohmic and cut in each resistor. Is quite easy to know what the output is depending of the input of the transistor. So we have the last case. In the last case, both transistors in the base part are in ohmic because they have 1 at their gates. So if the load transistor are in ohmic, the complementary transistor, the PMOS, are going to be in cut. And again, we are going to have a 0 because in the load part, both transistors are cut. There is no way for the supply voltage to reach the output. But here, ground can choose this way or this way. So it's going to be able to reach the output. So the output is going to be ground, that is 0 volts, that is a logic 0. So again, we have here the opposite of the OR gate, that is the NOR gate. This is a CMOS NOR gate. NOR gate. Okay. So now I'm going to tell you a method that you can follow to design any kind of logic function. I'm going to delete this. Okay. So we are going to focus at the base part of the CMOS and NMOS technologies. If we put transistors in the base in parallel, we are going to implement the logic sum of the inputs. Instead, the logic sum negated. Okay, if we put the base transistor in series, we are going to have the logic product of the inputs. Okay, remember that in parallel the components share the same connections, and in series the components are put one after the other. So we are going to see an example of this. For example, we are going to design an NMOS NAND. Yes, allow me to clear this. Okay. An NMOS NAND, an AND is the opposite of the AND. This is AND, so an AND is going to be the opposite, just negating the operation. So we are going to, as I said, we are going to design an NMOS NAND. Now the input has to be in series. Remember that to implement an AND, the logic product, we have to put the transistor in series. So the base part is going to be like this. This is an NMOS NAND, okay? One transistor and the other. They are NMOS because we have an NMOS technology, and we are going to have one input and another input. This is the gate, the source, the drain, and in the load part, in an NMOS technology gate, we always have a depletion MOSFET, like this. This is gate, drain, source, voltage, supply voltage, and here we have the ground. Okay, so we are going to analyze the circuit as we did with the previous ones. So we have 4 combinations, and we have 3 transistors. Transistor A, transistor B, and transistor C. And the output is here. So the combinations are these ones. So now we are going to check what happens according to these combinations. So the first combination, in the base part, we have 0 in both gates of transistor A and transistor B. We know that when we have here a 0, they are in cutoff. So when the base is in cutoff, we are going to look at the table in the InMOS case. In the InMOS case, when the base is in cutoff, the load part is in ohmic. So this is going to be in ohmic. What happened here? That the output is going to be 1. Why? Because we are cutting these ways, and we are this transistor always with a channel created. So the supply voltage is going to reach the output. What happens in the second case? In the second case, we have a transistor A in cutoff, and the other have a channel. Okay, so transistor A in cutoff, and the other is going to be conducting. It's going to be conducting in ohmic, because in his gate it has a 1. So it's in ohmic. So the other transistor is going to be just give me a second. It's going to be in ohmic as well. Not in ohmic. This is going it's going to be, the other transistor is going to be in ohmic. Yes. Why? I'm going to explain you why. In this case, the A transistor, the output is going to be 1, and I'm going to explain everything. In this case, A transistor is in cutoff, So here we have this branch cat. So it doesn't matter what is the state, what is the operation of B transistor, because the base part is cat, is open. The circuit is separated from the load part. What the transistor in the load sees, what the NC transistor sees, is that the base part is in cat, okay? Because the branch is broken. So if we have a look here, if the base is cut off, the load is going to be in ohmic. So the base have to be in ohmic, both transistors, in order to have the load in saturation. So in this case we have the base in cutoff, so the load transistor is going to be in ohmic. So NC is in ohmic here. In this case we have exactly the following, the following not exactly the same, sorry, but A transistor is in ohmic, B transistor is in cat, and again the C transistor is going to be in ohmic. We have now now we have that this transistor is cat. So again the base is cat because the branch is broken. So we have exactly the same case. The supply voltage can use the channel of the depletion MOSFET to reach the output. So we have a 1. And in the last case, both transistors in the base are in ohmic. So if both transistors are in ohmic, the base is in ohmic, and the load is in saturation. When the load is in saturation, this voltage is going to be 0, so the output is going to be 0. So this is in saturation. Sorry, this is going to be in saturation, so this is going to be 0, and this is going to be 0. So the output is going to be 0. And this is the exactly the opposite case, this output of the AND gate. So this is a NAND gate, as we see here. So we are going to build now a NAND gate, but using a CMOS technology. In a CMOS technology, I told you that in the InMOS and the CMOS technology, the base is exactly the same. So I'm going to keep the same base. And I'm going to design the load part of this gate. Remember that we need the complementary part of the base. So we need two transistors that are going to be PMOS, and these transistors are connected in series, so the load has to be connected in parallel. So in the CMOS case, we have two transistors, but now connected in parallel, sharing the same nodes at their terminals. PMOS, PMOS, the output connected. They are connected to the same input, the source, the gate, and the drain. This is going to be the complementary A PMOS and the complementary B PMOS. So we are going to analyze what happened now. The 4 combination, and the 4 transistors. So now, in this case, in the case of the CMOS, it's much more simple, because if the base is in cat, the load is in ohmic, and just the opposite, and vice versa. So in the first combination, we have 0 at the gates of the NMOS A and B, so they are going to be in cutoff. So if they are in cutoff, their complementary are going to be in ohmic. Remember that from this table. Okay? So we have in this case that the output is going to be 1. Why? Because we have these ways closed, but these ways are open, so the supply voltage can reach the output following this way or following this other way. So in the following combination, A is 0, so A is closed, is in cutoff, and its complementary has to be in ohmic, just the opposite. The B NMOS transistor have 1, so it's going to be in ohmic, and his complementary has to be in cutoff. In this case, we have our a 1 again. Why? Because now this way is closed, so ground cannot reach the output because it's closed here. But the complementary B is closed, but the complementary A, is open. So the supply voltage can use this way to reach the output. In this case, we have a 1 in A, so A is ohmic, and its complementary have to be in cat. We have a 0 in B, so it's going to be in cat, and its complementary transistor have to be in ohmic. In this case, we have a 1. Why? Because we have this transistor cat, the B of the base, so ground cannot reach the output because it's cat here, the channel. And we have cut in the load port the A transistor, but the supply voltage can use the other way to reach the output. So the supply voltage is a 1. And the last combination, in the last combination, both A and B in the base are in ohmic because they have a 1 at his gate. So their complementary transistor have to be in cat. In this case, we have a 0. Why? Because in the load part, both transistors are cat, so the supply voltage cannot reach the output. But here, in the base part, both transistors are in ohmic, so they have channel. So the ground can use both channel to reach the output. So ground is 0 volt, that is logic 0. And again, we have a NAND gate, a CMOS NAND gate. As you can see, we need more transistor in the load part than in the case of the NMOS family, but we have as well less consumed when using CMOS, as we saw in the last lesson. So now I'm going to put the following example, but I'm going to clear this before. I want to delete this, but here. So imagine that the professor has a really evil mind, and the professor asks you to design a circuit with the following function. The logic function that the circuit has to implement is this one: A, B, C with the logic product plus D all negated. How would you do this? Well, we have to analyze the function. We need to know if the technology that we have to use is NMOS or CMOS. In this case, imagine that you have told to implement this with a CMOS technology. So how do we proceed with this function? We can identify that we have logic products and logic sum. So we can focus, for example, in these three inputs that are multiplied with the logic product, and the result of these three inputs is summed with the logic sum to another input that is D. Okay, so we are going to need 4 transistors in the base and another 4 transistors in the load part, because they are the complementary part. Why 4 transistors? Because if you remember, we have the inputs connected to the gate of 1 transistor. So we are going to proceed. A, B, and C are multiplied. So if we want to implement logic multiplication, we have to connect these 3 transistors in series. So we are going to draw 3 transistors in series. So here we have 3 NMOS transistors that are going to be connected to the 3 inputs. Input A, input B, and input C. I'm going to make the pencil a little thinner. So we have these 3 transistors in series, so we have the multiplication. And these 3 inputs are summed with a D input. Since they are summed to the D input has to be in parallel with them. We can connect this. It's easier to see this way. We can connect this to the ground. And here in parallel, as I said, we have the D inputs. So now this base is implementing, A, B, C plus D, because these are in series. This one is in parallel with the previous ones. So now we have to implement the complementary part, because we are working with a CMOS technology. So the complementary part of these transistors have to be in parallel, because these 3 inputs are here in the base in series. And this input, this complementary transistor of the input D, has to be in series with these 3 transistors, because here in the base is in parallel. So we are going to add the PMOS of the input, and we need to put this in series with the other transistors that now are going to be in parallel. So in parallel they are going to share the same nodes. Remember, they are PMOS. And here we have the supply voltage. So this is the complementary, for example, of C. This is going to be the complementary of B, and this is going to be the complementary of A. So this circuit implements this function. We may do the same as for the other circuits, but we are going to have a lot of combinations here. Okay, we are going to have 16 combinations, a lot of transistors. So you can do it if you want to check that this circuit works, but I can assure you that the circuit works. So just combining this transistor in series or parallel, we can make any logic gate we want. What happens if I want this function but not negated? We can do the following. We can take the output and we can connect the output to, for example, an inverter, a CMOS inverter. As you can remember, that was this way. So now the output of this circuit is going to be the negation of this, that is equivalent to remove this. So you can connect a lot of logic gates one after the other and have the function that you want. What happens if you want to implement this function but using an MMOS technology? Just let me delete this. If we want to use the MMOS technology, we can remember that the base is going to be exactly the same, but the load is different. How is the load? Really simple. The load is like this. Sorry. With the depletion MMOS connected this way. So this is exactly the same function but with MMOS technology. So this is a thing that can fall in an exam. I may ask you to, I give you a function like this one, for example, and I can ask you to design the circuit that implements this function. I have to tell you if you have to use MMOS or CMOS, or I can tell you that you can use the one that you prefer. So this is a typical thing that can be asked in the exam. Or I can give you the circuit. You have to analyze if the transistors are in parallel or in series, etc., and extract the logic function. Okay? I think that this is quite simple. Once you know how to use the CMOS and the MMOS families and to identify if transistors are connected in parallel or in series, it's a quite fast thing to do. It's very mechanic. You don't have to think a lot. You have to know this. You have to know this table. This is a basic thing in order to can design this kind of logic gates. So this is the last part we are going to see of the topic 3. So now we are going to start with the topic 4. Just give me a second to. Okay, this is the topic 4. We are going to create a new. We are going to create a new board. This is the first time I use this program, so I hope you to be patient. Okay, so we are now in topic 4. Topic 4 is going to be the first introduction to digital system. It's a quite important topic because it's going to set the foundations to help you understand digital electronics. We are going to see the following things. We are going to study numeral systems using computer science and how to encode information using this numeral system. We are going to learn about the Boolean algebra. That is the mathematical framework, the mathematical base that we are going to use to work with digital circuits. You have to manage perfectly Boolean algebra, because you are going to use this algebra to to manipulate function, to create function, to simplify function, etc. And as you just have seen in the previous examples of the gates that we have seen in topic 3, functions are translating into gates, and gates are translating into connection of transistor. You know, we can represent a function with more or less gate. If we use more gate, we are going to need more transistor, so the gate is going to be more expensive, the gate is going to be less efficient, it's going to be bigger in area, so the integration is going to be worse. So Boolean functions are really important because they are going to be translated physically in logic gate and transistor. So we have to obtain really good and efficient functions that work with zeros and ones, that are the Boolean functions. This is the specific contents that we are going to see in this topic. We are going to see the numeral systems that you are familiar to, even if you don't know yet, how to represent integers using digital codes, and another codes, numeric, alphanumeric, and maybe error detection. I don't know if we are going to see the error detection yet, because we are not really good in time this semester with all the public holidays that fall in the subject slots. So, well, here we have the Boolean algebra, the definition and actions, their properties, and how to work with variables and Boolean functions. And finally, we are going to see logic gates. So, here we have a binary signal. I told you that the voltage itself is an analog signal because it can take any value, but here we are not interested in analog signal. From this topic and on, topic 4 until the end of the subject, we are going to forget about these intermediate values because we are not interested in them. We are only interested in ones and zeros. So we are going to suppose that the zeros are right zeros and the ones are right ones that are inside the interval to be considered ones, and zeros are going to be in the interval to be considered zeros. So we are going to forget about these voltages and these things. We are going to work only with zeros and ones because zeros and ones are the variables that digital systems work with. So in the digital systems we have two kinds of systems. The first one is the combinational system. That we are going to study in topic 6. Topic 6 is going to be devoted only to combinational system. In a combinational system, the output, I cannot write here, sorry. Okay, we can ignore this, okay? So in the combinational system, the output is going to depend only just let me to stop the recording to fix this thing, and I'm going to continue in some minutes. Thank you.